with the Licking County Engineer's Office. My title is Bridge Engineer for the county. And I'll let Ron introduce it.
My name is Ron Maddox. I work with Henderson Associates, which is a private consulting engineering firm. I'm in charge of transportation and been doing bridge design for a little over 30 years. So, a resource.
Okay. Tonight we're going to go through, first off, we're going to start with just a little general presentation on civil engineering and bridges. Civil engineering, obviously, is a branch of engineering that deals with structures. You know, the design, construction, inspection, maintenance of dams, roads, bridges, buildings, any kind of infrastructure project that's out there. Water lines, sewer lines, all kinds of stuff. But tonight, let's just focus on bridges. So, why do we build a bridge? I get some answers on why do we build bridges? Bridges are expensive. Roads are a lot cheaper. It's a lot easier to build a road than a bridge. But why do we need bridges? We have to cross natural or man-made obstacles, streams, rivers, other highways, valleys, other railroads. Bridge basics. We have a couple, generic definitions for bridges. One is a span. A span is the distance between bridge supports. It could be two abutments, it could be an abutment or a center pier, but it's that distance. That's what's called the bridge span. Compression is a force that acts upon the bridge. Compression is think of something pushing together. So piers are mainly in compression. When piers have to support the weight of the bridge and what drives across it. So when a truck drives across the bridge, it pushes down on the bridge, and that puts the piers in compression. Tension is the force of the acting of wanting to pull something apart. When you have a suspension bridge or a cable stay bridge, those cables are mainly in tension. They're wanting to be ripped apart, and that's what the force of acting. Scour is an act of nature. Scour is the force of water that acts upon the bridge. Scours can be very dangerous, so we have to watch out for it. When the velocities of the water gets up, or when the water levels goes up, it can wash out the dirt and the foundations around the bridge, and that's the act of scour, and that can cause the bridge to collapse. We normally protect it with large rocks, or we pour concrete, or put in steel to protect the foundation substructure. We have wind loadings on bridges. Normally not smaller bridges. Wind loadings don't really come into effect unless the bridge is relatively long. So cable stay bridges, long suspension bridges, those are the types of bridges where wind loadings become very important. And we have to do models of those bridges, put them in wind tunnels, and make sure that the bridge design can handle the wind loadings. And resonance, that is the act of its vibration. So once you start to get a vibration in a bridge, if the resonance builds up, the vibration can continue to grow upon itself and it can damage the bridge, or even in some cases cause a bridge to collapse. The history of bridge construction. So bridges have been around, before we had any types of material and stuff. Bridges could be a log. The Romans built many bridges, a lot out of stone. That's the material they had available. They built stone arches all across Europe for the transportation of goods, soldiers. Even some of these were built to transport water through the aqueduct system. It's a picture from a bridge in England. This is the first cast iron bridge built. Cast iron is a pretty weak metal, pretty brittle, but that's what they had in the day back in the 1779. That's what they had, and that's what they used, and it worked. These types of bridges would never stand up to the vehicle traffic we have today. This is no longer has any vehicles driving on it. It's just for pedestrians and stuff. The materials we use today are steel and concrete, high-strength steel and concrete. These types of materials can handle the amount of freight that we transport nowadays with the rail freight and all the trucks on the roadway. Types of bridges and materials. You have arch bridges, truss bridges, beam bridges, suspension bridges, and cable stay bridges. That's the main grouping. Most bridges would fit in one of those categories. First is an arch bridge. An arch is like the Roman bridge I showed you a little bit ago. It's the oldest type of bridge. Besides the tree. An arch bridge directs the force in a semicircle and down through the piers. So that force is transmitted across the top and then down into the piers and down into the foundation. Without that center stone, the bridge would collapse. That's the keystone. That's the most important part of the bridge. Until that keystone is in, the bridge doesn't have that much strength. But once the keystone's in, these types of bridges are very strong. They last a long time. As you can see, with a lot of the Roman bridges, they're still around. Some pictures of some other ones. You can have multiple arch stone bridges.
Do you know one around here? I can think of one offhand. Cherry Valley Road. Over Raccoon Creek. Used to be an aqueduct. It is all stone arch.
Beam bridges. These are pretty simple bridges. These are probably the most common bridge to build. You got supports and then just steel or concrete beams across. Here's a couple examples of beam bridges. These are the most common, cheapest way to build. You can get a pretty good span length out of these. Pretty easy to maintain. These are the most common. Truss bridges, made with a bunch of combination of triangles. It's more rigid than a single span. You can get some longer lengths out of it than some of the smaller beam bridges, but truss bridges you have to watch because some of the members are very critical, and if some of the members fail, the whole structure can come down. So you have to be very careful and inspect them and make sure that you keep them painted and you keep the corrosion off them and stuff like that. They serve their purpose, but you do have to watch these a little bit more than a steel beam bridge. Example of a truss. And we have, this is a Seven Hills Bridge. It's eastern Licking County. It's above the river tracks out by Hanover. So this bridge is still there. It's going to be replaced in a couple of years. It's in bad shape, but we're going to donate it to the Boy Scout camp out of Camp Fallen. So we're going to move it out there and they can use it, but it's past its useful life for a truck traffic. Suspension bridges. Suspension bridges are built for very long spans. They're very expensive, but when you don't have space to put center piers in the water, they serve their purpose. It's to create long spans, and so the force here is you have two vertical towers. Cables are draped across those, and the load is transferred through the cables, through the tall towers, and then to anchors into the pin. These are like the bridges you see here, like the Golden Gate Bridge, like this bridge. These are called suspension bridges. They're very expensive, but they do serve its purpose to create a very, very long span of it. Cable stay. Cable stay is similar to a suspension bridge, except the cables aren't anchored in, and all the force is put into the tall column. With suspension bridges, these types of bridges do travel over, they can span long distances. We have a couple here in Ohio. We built one in Toledo a couple of years ago that spans the Maumee River Bridge, and that was built that way you can keep the river open for boat traffic and stuff like that. So, and this is an example in Europe of a very long cable stay bridge over a deep valley, and one of the longest ones in the world, cable stay bridges, multiple span. But this is you can get some very long spans of these. Learning from failure. So we go through a couple things that have happened over the years, and the engineering community learns from our failures, and we change our practices and our procedures to prevent tragedies in the future. The first was actually here in Ohio. It was the Silver Bridge across the Ohio River. It was a suspension bridge that it was built like in the 40s, and it collapsed in 1967. It was a suspension bridge this type, and the bottom left shows you there's a pin, and it had steel bars that connected to that pin. Well, one of those failed, had developed a crack, and eventually separated, and the entire bridge came down. We call it fracture critical. One of these things could fail, it could bring down the entire bridge. These are the bridges that you really have to watch. And ever since this bridge collapsed, this was the birth of the annual bridge inspections process. Federal Highway, or the Congress got involved, and they said we will inspect bridges every couple of years, and we will make sure they're safe for the traveling public and all that. But this collapse is why we inspect bridges yearly now. So that's one of the lessons learned: redundancy and annual bridge inspections. Next one is bridge in New York. This was a scour failure. Water came up and washed out the foundation, and the bridge collapsed. Since that time, these are types of scour. This is what water can do when you don't protect your substructure from scour. Water is very powerful. It can wash out where that person's standing. That should all be. There should be rock and aggregate stuff where he's at. That's not good. And the same with the other two pictures. We do scour inspections when we do a standard bridge inspection, and if we're starting to get erosion, then we bring in big rock and dump it and fill in holes. And then the last one was, this is the I-35 bridge that collapsed. This was in Minnesota. We got a video of this, but this is a couple things here was there was a design issue and also an inspection issue. And the design issue, it was column gusset plates, but the top left, those pieces of steel that hold all the other members together was too thin, and it was designed too thin, and it lasted a long time, but over time stuff starts to break down, it starts to corrode, and on an inspection it might have been able to catch some stuff, but that's one of the things now is after that class, Ohio went and looked at all their bridges of this type and inspected them to make sure that the gusset plates weren't buckling under the weight and stuff like that. And if anything needed corrected, they did the corrections. But design and inspection of the members that are very critical to this bridge design is what we learned. This is a picture. This is the newest bridge in Columbus. This is their signature bridge now in downtown Columbus at Carriage Main Street. They just opened it last year, I think, 2 years ago. Okay.
really is great stuff, background information for you, but you're not going to be able to work in steel. You're not going to be able to work in concrete. You've got tiny little toothpicks and glue, but the principles are the same. Compression. If you take that toothpick and squeeze it at the ends, it's going to snap. You've all done that. We've all done that. If you can pull it apart, if you're strong enough and you can hold on to it enough, it will pull apart. But it's stronger in tension than it is in compression, unless you can match it up and put bunches of them together so that it won't bend. So if you add strength to it, that's what you're getting at. So you've got a couple of options for your bridge, thinking of the compression and thinking of the tension and how it's going to fail. One of the things he talked about were all the failures. And when we've had failures of bridges, we've learned lessons from them and moved on. Most of the classes and most of the folks that have competed in this have done multiple bridges and have failed them. So you probably want to try that. Try a design, work it out, go online, get some ideas, try it, fail it, and find out which member broke. Does that one member need to be stronger? Probably. Or is the next one right up beside it going to fail right after that? So there's a bunch of principles you're going to need to learn. As far as the competition goes, you got a span that you've got to cross. It's a little difficult in this to see. This is essentially your piers, or your buttons, need to be out here, and it's going to come up and over the top. We're going to want to push our little boat underneath, so you have to have so much clearance, and then we're going to load it with this block. In the handout, there's some drawing or the photographs of this actually happening. So I'll be able to take my little car and drive through there, except that your bridge is going to have a little hole in the middle. We're going to run this rod up through it, put this block on it, and then we're going to load it from the bottom. Last year, the year before, we actually used a bucket, filled it with sand or steel plates, and loaded it up and then measured how much weight there was at the end. We're looking at a different way of doing that, where we have an actual tension cable that will load it more mechanically. So that may or may not be, but your loading system is still the same. It's that one little block that you have in the middle of your roadway that we're going to load it against. Now that's the bridge, and there's several aspects of the bridge you need to be careful of. The weight. You don't want to gob it up with glue, because that's going to add weight, because the weight's important. There's a strength to weight ratio that will be judged on. Also, you're going to have judge on your cost effectiveness, and we deal with this all the time. All of the bridges that are out there were justified in the cost. Even the big suspension bridges, they cost billions of dollars to build one of those, to design it, build it, maintain it. You're able to justify that based on need. But there are bridges out there that we can design, but the cost is so extravagant that they're not built yet. There are designs out there for a bridge that goes from Alaska to the Soviet Union, across the Bering Strait. It's been designed, it can be done, but it would cost so much money that you just can't do it. So your bridge has the same type of issues. What's your cost? And each toothpick costs so much, and so much glue costs so much, so you have cost effectiveness. And we deal with that as engineers all the time. Another different example of that is, everybody remembers the flooding, the hurricane in Louisiana, New Orleans. The flood system there was not high enough, strong enough to withstand that hurricane. We do not design for an ultimate hurricane. We design for a certain level, and we accept the risk that beyond above that, we're going to pay for that. That's the way we do just about everything. We cannot afford to make it perfect and absolutely able to carry everything. And you you've got the same situation. What's the most cost-effective way to design your bridge? So that's about the bridge. The other thing you'll note in here is your presentation is just about as important as your bridge. I would expect you're going to want to practice, get up and try it, see how long it takes. Those that practice seem to win. So,
one of the things that is new this year, if you haven't gotten this update, is we worked with Weathervane, and we, on Wednesday of next week, 5 to 6, the same time as this presentation, Adam from Weathervane will be here to talk with you about presentation skills and talk with you about setting up meetings with them to work on your presentation skills. So we did make that available for you this year as well.
And I would support that because in my role, I have to do presentations all the time. I don't just get jobs. I have to go out and earn them. I have to tell them why they should select me to do a job. So I have to have my skills, and so does everybody else. So your competition there also. With that, I'm going to open it up to questions.